Hey everyone, and welcome back to AI.Code.Cast. We're going to do a deep dive today into a problem that's really colorful and really challenging. It's called remove boxes.
Oh, yeah. I love
So
it.
imagine like a line of boxes. Each box is a different color.
Okay.
And our goal is to figure out how to remove these boxes to get the highest score.
Okay.
But here's the thing. You get more points if you can remove like a longer stretch of boxes that are all the same color.
Right. Yeah. So it's a kind of strategic,
It's
right?
like Tetris, but with points.
Yeah, exactly. It's like Tetris, where, you're trying to kind of plan ahead and
Yeah.
see those patterns, right, to put those big combos.
Yeah, exactly. So let's say we have a line of boxes, and it's like red, blue, red, red, green, green.
Okay.
How do we even start to, figure out the best way to remove them?
That's a good question.
I'm already feeling, a little overwhelmed just thinking about all the possible combinations.
Yeah. No, it can be overwhelming. One way to think about it is, you could just try everything. We could literally just list out every single possible sequence of removing boxes and calculate the score for each one.
Okay, so, if I remove the first red box, then the blue box, then the next red box, calculate that, and then I try a different sequence.
Exactly, yeah.
And then another, and another, until I've tried every single possible combination.
Yeah, and that sounds pretty tedious.
Incredibly tedious.
That's the problem. That's what we call the brute force method, right? But the problem is, let's say you have even just 10 boxes.
Yeah.
The number of possible sequences grows incredibly fast, right? It's
Yes.
like a factorial problem. So with just 10 boxes, we're talking about millions of combinations.
Whoa. My computer would probably, melt trying to calculate all that.
Exactly.
So brute force is not going to work.
Yeah.
There's got to be, a smarter way to solve this, right?
Yeah, you're absolutely right. Brute force just becomes impractical as the number of boxes grows. And that's where we need a more elegant solution, a more efficient solution. That's where dynamic programming comes in.
Okay, I've heard of dynamic programming. I always get a little intimidated by it.
Yeah.
Can you break it down for us? What's the core idea behind DP?
Yeah,
And how can it help us solve this remove boxes problem?
absolutely. So dynamic programming, really, it's all about breaking down a problem into smaller overlapping sub-problems, right? So it's kind of like a divide and conquer strategy, but with a twist, right? So instead of recalculating the solutions to these sub-problems every time we encounter them, we store the results and we reuse them whenever needed.
Oh, so that's where the dynamic part comes in.
Exactly, yeah.
It's like remembering where you parked your car so you don't have to, search the entire lot every time.
Exactly, yeah. That's a great analogy.
So we're saving ourselves a lot of work.
Exactly. So now, in the context of remove boxes, imagine we have this function, and this function can tell us the maximum score achievable for any given segment.
Of boxes, right. So let's call this function dpij, where I and j represent the starting and ending index of that segment.
Okay, so dp05 would give us the maximum score
Yeah.
for the whole line of boxes, if we have 6 boxes, let's say.
Exactly.
And dp24 would tell us the maximum score for just the subsegment, from the 3rd to the 5th box.
Exactly. You got it.
Okay, I'm following so far. But how does this function actually work?
That's a great question. So this DP function, it uses recursion.
Right.
Right. So it calls itself with smaller and smaller segments
Okay.
until it reaches what we call a base case.
Yeah,
right?
talk.
And the base case is a very simple scenario that we can solve directly.
Yeah.
So for remove boxes, this base case could be just a segment with one box.
Right, because if there's only one box, you only get 1 point.
Exactly. Yeah.
So how do we go from these simple base cases
To solving the whole problem. How does this DP function actually figure out the best way to remove the boxes?
Yeah, that's where the kind of magic of dynamic programming happens.
Okay.
So let's break it down. So for any given segment, right, this DP function has to consider a couple of key scenarios. So first, it can remove any consecutive boxes of the same color at the beginning of that segment.
Okay. So if our segment starts with 3 red boxes,
Yeah.
we can remove them right away, get those points, and then focus on the remaining part of that segment.
Exactly. And that's where, the recursive nature of DP comes in. So after removing those initial red boxes, right?
Yeah.
We're left with a smaller sub-problem, right? The rest of the boxes.
Yep.
So our DP function, it calls itself again, but this time with the updated starting index to figure out the best way to remove the remaining boxes.
So it's like we're breaking down the problem into these little bite-sized pieces.
Exactly.
Solving each piece.
Yeah.
And then combining the solution to get the answer for the whole segment.
Exactly. Now, the second scenario that the DP function has to consider is a little bit trickier, right? So what if there are other boxes of the same color as the first box, but they're not consecutive? So we need a way to explore the possibility of combining those boxes later on.
That is more challenging. So like, let's say our segment starts with a blue box, then has a red box, and then another blue box further down the line.
Yeah. Exactly.
How does the DP function handle that?
Yeah. So in that case, the function would need to explore the possibility of removing that red box.
Okay.
Right. Which would then allow us to combine those two blue boxes into a group of two, right?
Right.
So to do this, it would recursively call itself.
Well,
the subsegments before and after that red box.
Okay. So it's like looking ahead and saying, hey, if I remove this box now, it might open up a better opportunity to create a bigger group later.
Exactly. So you're thinking ahead, right?
Yeah.
Exactly. So the DP function explores all these possibilities, right? Calculating the potential score for each scenario. It's kind of like, branching out and exploring different paths, right?
Right.
But with the key difference that we're remembering the results of our explorations.
Right. That's where memorization comes in.
Exactly. Yeah.
Right.
Yeah.
We store the maximum score for each subsegment we've already calculated.
Right.
So we don't have to redo that work if we encounter the same subsegment again.
Exactly. You got it.
It's like having a cheat sheet for a recursive exploration.
That's a great way to think about it.
Okay.
That's what makes dynamic programming efficient, right?
Yeah.
Without memorization, we'd be recalculating the same things over and over.
Right. Just like brute force.
Exactly. Yeah.
Okay, so I think I'm starting to grasp the power of dynamic programming here. It's like we're strategically exploring this vast maze of possibilities.
Right.
But we're using breadcrumbs,
Yeah, I love that.
to avoid getting lost or going in circles.
I love that analogy. And those breadcrumbs are the memoized scores for each subsegment.
Right, exactly.
They guide our exploration and ensure that we're always making progress towards finding the optimal solution.
Okay, this is fascinating stuff. So we've got this DP function. It uses recursion, memoization, and it cleverly explores to find the highest score for any segment of boxes.
Exactly.
But how do we actually put it all together to solve the whole problem?
Right.
Where do we start?
Yeah, so we start with the simplest subproblems.
Okay.
The ones that we can solve directly.
Okay.
So in our case, that would be the segments consisting of just a single box.
Okay.
So we know the maximum score for that is just 1.
Right, 1 point.
Exactly. So we seed our memorization table with those base cases.
Okay.
And then what do we do?
Yeah, what do we do?
Well, we can start calling our DP function for larger and larger segments until we reach the entire line of boxes.
Oh, okay. So we just keep building up.
Exactly. And that's what we call a top-down approach.
Calm down.
Right.
Okay.
We start with the big problem, break it down, solve the smaller problems, combine the solutions.
Okay.
But there's another way to do it. We can use what's called a bottom-up approach.
Oh, interesting. So instead of starting with the big problem and breaking it down, we start with the small problems.
Exactly.
And then we build up.
Exactly. We build up to the solution.
Okay. I'm intrigued.
Yeah.
Can you walk me through how this bottom-up approach would work for remove boxes?
Absolutely. So in the bottom-up approach, we still use our DP function.
Okay.
We still use our memorization table.
Okay.
But the order in which we fill up that table is reversed.
Okay.
So we start by calculating the maximum scores for all segments of length 1, then length 2, then length 3.
Oh, okay.
And so on.
So we're building a pyramid.
Exactly, yeah. A great analogy.
Starting with the individual blocks at the bottom and working our way up.
Exactly. So just like building a pyramid, each layer in our bottom-up approach relies on the stability of the layers below it.
Okay.
We're using the solutions for smaller segments to build up the solutions for larger ones.
Okay. I think I'm starting to see the beauty of the bottom-up approach. It's systematic, it's elegant, and it feels like we're building something solid and reliable. But how exactly do we handle, like, the grouping of boxes in this bottom-up world?
Right.
Like, remember how we said that removing longer stretches of the same color gives us more points?
Right.
Is the bottom-up approach, like, particularly well-suited to take advantage of that scoring system?
It is.
Okay. I'm curious to see how.
Yeah. So in the bottom-up approach, we can iterate through our boxes and identify consecutive groups of the same color, right?
Okay.
So for each group, we can pre-calculate the maximum score achievable if we were to remove just that group.
Okay. So we're not grouping the boxes physically, but we're, like, pre-calculating the scores for all the potential groups.
Exactly.
And then we could use those as, like, building blocks.
Exactly. It's like having a set of, like, prefabricated components that we can assemble in different ways to create our final masterpiece.
I love that analogy. Okay.
Yeah.
This is great.
Yeah.
So, yeah, we're going
to take a break. And when we come back, we'll dive deeper into this bottom-up approach.
Awesome. This is AI.Code.Cast, and we'll be right back. So by pre-calculating those group scores, it's like we're already setting ourselves up for success.
Yeah.
When we get to the later stages of our bottom-up approach.
Exactly. It's like we have, like, a blueprint, right?
Yeah.
That guides our construction process.
Okay.
So we know the best way to handle each individual group. And now we just need to figure out how to combine them with the rest of the boxes.
So how do we actually, like, combine those pre-calculated scores with the other segments?
Right.
It feels like we're juggling a lot of different pieces.
It can feel that way, but remember, the bottom-up approach is all about building things up systematically.
Right.
Right. So let's say, like, we're working on a segment that spans from index I to index J in our line of boxes.
Okay, so DPIJ would represent the maximum score for that segment.
Exactly.
Okay.
Now, within that segment, we might encounter several of our pre-calculated groups.
Right.
Right. The key is to iterate through all possible split points within that segment.
Split points, what are those?
Yeah, so a split point is basically an index, let's call it K, that divides that segment into two smaller subsegments.
Okay.
One from I to K and another from K plus 1 to J.
Okay, so we're trying out all the different ways that we can divide up our segment into two pieces.
Exactly.
Yeah.
And for each split point, we calculate the potential score.
Okay.
Right? And so how do we do that? Well, we take the maximum score for that left subsegment, which we've already calculated right in the previous steps of our bottom-up approach.
Right, so that would be like DPIK.
Exactly.
Yeah.
We do the same thing for the right subsegment, DPK plus 1J.
Okay.
And then, crucially, we add in the score for any group that spans across that split point.
Right, okay. That's important, right?
Yeah.
We need to account for the points we get from removing those larger groups.
Exactly.
That might be broken up by our split.
You got it.
Okay.
By considering all those possible split points and factoring in the group scores, we're making sure that we're exploring every single way to maximize our points.
I'm seeing the elegance of this bottom-up approach.
Right.
Like, we're breaking down the problem into these manageable chunks, pre-calculating scores, strategically splitting our segments,
Yeah.
and then ultimately, like, building up our solution step by step.
Exactly. And the best part is that both the top-down approach and the bottom-up approach, when implemented correctly, will give us the same answer.
Wow, okay.
The optimal solution.
So it's like two paths leading to the same treasure.
Exactly. Yeah.
We can just choose whichever one makes more sense to us.
Exactly.
Or explore both.
Yeah. Yeah. The key takeaway here is dynamic programming gives us these really powerful tools to solve problems, like remove boxes, right? It encourages us to break things down into smaller pieces, to think recursively, and to just find these elegant solutions.
I feel like I've gained like a new appreciation for dynamic programming.
Yeah.
It's not just about like memorizing algorithms.
Right.
It's about understanding the principles behind them and how to apply them creatively.
Yeah.
So this has been an awesome deep dive. I feel like I've learned so much.
Good, good.
And I want to thank you for walking us through this.
It's been my pleasure.
And to our listeners, keep those coding brains buzzing, and we'll catch you next time.
See you next time.
For another deep dive on AI.Code.Cast.
So it's like we have this blueprint, right? These pre-calculated scores for each group.
Exactly.
And that helps us figure out how to best combine them later on.
Right.
Okay, so how do we actually go about combining these scores with the other segments? It still feels a little like we're juggling a lot of pieces. It can feel that way, but remember, it's all about building things up right, systematically, in the bottom-up approach. So, like, imagine we're working on a segment that goes from index I to J in our line of boxes.
Okay, so DPIJ represents the maximum score we can get for that segment.
Exactly. Now, inside that segment, right, we might see a bunch of those groups that we pre-calculated. The key here is to try all the different ways to split that segment.
Split it, like cut it in half.
Yeah, kind of. We call them split points. It's like an index. Let's call it K. That divides our segment into two small pieces, one from I to K and the other from K plus 1 to J.
Okay, so we're basically saying, what if we divide the segment here, or here, or here, and trying out all the possibilities?
Exactly. And for each split point, we see what the score would be.
Okay, how do we do that?
So we take the maximum score for that left part, which we already figured out, right? Because we did the smaller segments first.
Right. That'd be like DPI, K.
Exactly. And we do the same thing for the right side, DP, K plus 1 and J, and then we add those together. But here's the important part. We also got to add in the score for any group that, crosses over that split point.
Right. Because if we split a group, we don't get as many points.
Exactly. So by looking at all the possible split points and adding up those scores, we make sure we're considering all the ways to get the most points.
Wow. Okay. This is really cool. It's so systematic. We're breaking things down, calculating scores, splitting things up, and building our solution.
Exactly. And the best part is, whether we do the top-down or the bottom-up approach, as long as we do it right, we'll get the best possible solution.
That's amazing. It's like two different paths leading to the same destination.
Exactly, yeah. Dynamic programming is all about giving us the tools to break down these problems and come up with really elegant and efficient solutions.
I feel like I've learned so much today. It's not just about memorizing the steps. It's about understanding the principles behind it and how to use them to solve all kinds of problems.
Absolutely. And the more you play with these ideas, the more you'll get comfortable with them.
Awesome. Well, on that note, we're going to wrap up this episode of AI.Code.Cast. A huge thank you to our expert. I learned a ton today.
My pleasure. It was fun.
And to all our listeners, keep those coding brains buzzing. And we'll see you next time for another deep dive into the exciting world of algorithms.